Hello and welcome to this video on revisiting gravity. We're going to revisit gravity, the concept of gravity, and we're going to look at it through three different sciences: our conventional science, divine science, which you've heard me talk about in previous videos, and a new one, Tartarian science. Why am I looking at this? Well, I've come across my calculations on global warming, and as we know, the global warming, we believe that the Earth has warmed up 1.4 degrees Celsius. So according to my maths, this makes the Earth has expanded in size by 0.5%. So therefore the circumference of the Earth has got slightly larger. And my maths has worked over 1 year, is now shortened by 30 seconds every year. So it's been quite happening for quite a while now, so our previous years should have been also shortened. However, our year is exactly 1 year to the microsecond and to the millimetre in time and space. And that's happened for 3,000 years continually, and through ice ages and hot and cold, the Earth has not changed. And our sundials, which are 3,000 years old, some of the Mayan sundials, still show the Earth exactly at the same time, without change. So, to me, there's some flaw in our solar model. And I believe we should go back to Galileo and his discovery of gravity. Now, it was Galileo who discovered gravity, not Newton, which everyone gets confused with. Galileo discovered gravity and the birth of the heliocentric model. So that's where we have to go back, and this is where revisiting this. Back to the start, back to 1590 when Galileo discovered gravity. I think that's where the problem is. This heliocentric model has got flaws in it. The Earth going around the Sun, okay. It goes on a 1 billion kilometre journey. It takes 1 year, comes back to the same spot within a microsecond every year to the millimetre. What's going on, you know? Is that possible for some object to travel that distance, 1 billion kilometres, and end up exactly the same spot in exactly the same time it take? Now, we've got 3,000 years of recorded sundials, and they haven't made 1 microsecond error. For 3,000 years, the Earth has not changed in time or distance it takes to make a year. And this concept of measuring time with this 1 second slip that they adjust the clocks to, we've got a clock travelling on the object we're measuring. They're talking about a relativity clock. The clock should be on the sun. If you're going to measure time, it should be the sun from the perspective of the sun, not the Earth. You don't measure the object travelling. Ridiculous. The concept of this 3D modelling, the sun's actually moving, so there's another vector involved, but yet we use 2D maths to explain the concept, back with Newton's maths. Sure, Newton was brilliant, the concept was good, but that's a 2D model. Our solar system is a 3D model where the sun is actually moving as well. You know, this is not what's going on. But this has got a flaw in it, so somewhere along the line they've had to change the narrative a little bit to bring in this frictionless spider's web of time to explain a non-existent force, you know, acting on a physical object. This is Einstein. How ridiculous is this? You know, a frictionless spiderweb of time is controlling physical objects. Oh goodness, you know, we had to believe all this rubbish. Now the elliptical orbit, that's a good one. Everything explains with elliptical orbits. It works with elliptical orbits. All the textbooks draw an elliptical orbit like this, you know, big ellipse. But yet, in reality, it's only 0.1% off a true circle. So to me, these planets are actually going in a true circle. 1% off a circle is, to me, that's a circle. Come on, give me a break. Ridiculous. Astrophysicists, astronomers, space agencies, these are intelligent people. They go to work every day under the pretense of this perpetual motion of an heliocentric model. Seriously? These people, intelligent people. We have intelligent people, doctorates in, astrophysics, yet they believe in perpetual motion. Okay, anyway. Oh, the other one, the big one, telescopes. There's an inherent flaw in them. Yeah, I had to invent a telescope. It took me 2 years or a year to invent a telescope. Didn't have a flaw in it. If you want to go to my video on the Plane telescope, I couldn't believe the errors I was making because there was this inherent error in the telescopes. Yeah, look, I feel like that little boy having to say that the emperor's got no clothes. There's something wrong with this heliocentric model, so let's keep investigating. Okay, so according to the textbook narrative from conventional science, in 1590, Galileo discovered gravity. And he discovered it by dropping 2 identical sized cannonballs from the leaning tower of Pisa, as the story goes. Now, we believe that one of them was lead and one was iron, but roughly in the 75mm size. And being round, and being of this weight, so anything virtually over a kilogram, you can ignore the effects of air resistance on anything over a kilogram. So virtually they were like dropping in a vacuum. And being round, there was no turbulence, unlike a square object, which would probably be influenced by air currents and give a different reading. So if we know in a modern day science, we use this vacuum test where we just put a ball bearing and a feather in a vacuum, extract the air, both released at the same time, the feather and the ball bearing will land at the same time. Experiment has been done hundreds of times, and yes, we know that for sure. However, the fact that they both hit at the same time, being different mass, created this conundrum where we have today, which has not been solved to my belief properly, whether the Earth came up to meet the cannonballs or the cannonballs fell towards the Earth. But that aside, Galileo was caught with the condition where it was very hard to measure this acceleration, so we're led to believe, for example, just in 1 metre fall, it takes about half a second, so it's pretty hard, we are led to believe, through the technology of the day, it would have been hard for him to measure the degree of acceleration. So he used a ramp, a ball on a ramp, and he used little bells that gave him a timing using a water timer in segments, and he worked out that the acceleration was 9.8 metres per second squared, as our modern day, what we know it as. But there's a lot of controversy about this so-called ramp, and it's probably one of the most underrated experiments of all time. Just a simple ramp, and has asked so many questions. And was Galileo actually looking for this acceleration? Now, he could have done it other ways, and much more easier ways, but he chose the ramp. Or was he looking for L? Now, L's this undefined time. We believe it, the length is Adam's first step. If you're a Christian, it's the first step that mankind made on the earth, which is approximately a metre. This 9.8 metres per second squared, we believe it, and I believe that Galileo thought it may have been a divine number, which would have been either 9.87 metres per second squared, which is pi squared, or it could have been 10, another divine number. So all depends on L. So have we got L right, the metre right? And if you want to go into the fairy tale of how they derived the metre, and that is a real fairy tale, that one. So interesting. What was he up to, really? So again, another interesting question. What is the actual gravity under the Temple Mount? What is it? What would we measure it today as? So a divine number or what? But anyway, we'll don't get sidetracked here, and we'll stay on the course of conventional science, and just assume that he was trying to find the acceleration by slowing down the ball on a ramp. And we need a very accurate ramp to determine this, unlike, I believe, Galileo may not have had. So let's reinvent this ramp, which we'll go to now, the ramp I have developed. Okay, this is my setup. On the lab bench there, you'll see the inclined plane in front of you. And in the centre of the inclined plane is the digital readout showing the X and Y axis. Also projected from the digital readout is a laser projecting on the wall showing a crosshatch datum point, which I'll explain at more accuracy in a later video. In the foreground you'll see the computer screen recording the data, and also over on the is my remote keyboard used to remote activate this without being too close to everything. So we'll do our first run to show you the operation. The first light there, first orange light, is the magnet release mechanism showing that the magnet is engaged. The first green light is when the ball first trips the first optical sensor, the first leading edge of the optical sensor. And this red light down here will show you when the ball bearing triggers the leading edge of the final sensor. So here's our first run. And the ball's reset. Just watch that bounce mechanism, just to give you an idea of the bounce. Now, if you're careful, just look at the digital readout changing as I roll the ball up to the next latching position. This system I try not to touch the ball too much because it overheats the ball and gives an erratic reading, but leaning over there, you might notice this digital readout. Just pressing on this will change our reading. So let's do another run. You might be able to catch that reading as well. Also, this computer screen is recording everything. Try not to touch the ball. Do another run. Hopefully you're looking at that, trying to catch that digital readout. It's 1.2 degrees at the moment, just the weight of this ball moving along it. Now, a lot of people haven't realised that just the weight of this ball can give you variations in your readings. Here's another run. Crazy how this thing is so precise. Later on in another video I'll show you a zirconian ball, which is half the weight of this steel ball, but we have to use a different latching mechanism because we can't rely on the magnet to release it. Another run. I'll just let that bounce for a bit just to show you the system settling down. So back to 1.5 degrees now, 1.3. This digital readout is very sensitive. Obviously Galileo didn't have anything this precise. We're only running 1 metre length and we're running 1.5 degrees at this stage. We can do that because we've got a G5 ball bearing, which is a very precise ball bearing, on a highly precision ground aluminium track. Again, Galileo wouldn't have had that in his day. He had had a longer run and he had to go for 5 degrees. We'll also increase this to 5 degrees later on, but our times will change. And I think any more than 5 degrees, and you'll find that the time, for Galileo, he would have been any higher than 5 degrees, his times would have been hard to catch because the ball would have been speeding up so quickly. On the screen you might be able to quickly see these readings that I've got. The first reading here that doubles all these zeros is for another clock, which I'll talk about in another video. It's important to run 2 clocks. In fact, we should be running 6 clocks. But the next reading is the time. It's all in seconds. This 0.052 is the time it transitions from the magnet release to the first optical sensor is triggered. The next reading is the time it took to go through the first optical sensor, which is 0.143 of a second. The next reading is the time and duration it took from the leading edge of this optical sensor to the leading edge of this optical sensor, which is 3.4 seconds. And the final reading is this transition through the next optical sensor, so that time that the ball takes to go through that final optical sensor. Alright, I think that's enough data. I don't want to get too much into this. This video is getting too long as it is, and we need to talk a little bit more at the results, so let's just finish up now. Okay, we'll just sum up now. Alright, we're running a 1.4 degrees angle, which ended up 30 millimetres at this end, which gave us an error between the runs of running between 3.42 seconds from here to here and 3.44 seconds. So end up with a 0.134 of a second deviation in 50 runs, which is 134 milliseconds, which is an extremely large error considering we're just rolling a precision ball bearing down a ramp, picking it up, putting it back in the exact same place, releasing it with a precision magnet and optical sensors, and we get an error of 4% over 1 metre. Okay, strange. We can improve on that, and later on in the videos you'll see me, I'll actually improve this, so I can fine tune the inclined plane and we'll get the error down. But initially this is over a metre. We're only talking compared to the Earth, so which brings us back to this divine science thing. Now when you put that in perspective, the Earth's journey of 1 billion kilometres travelling around the Sun in a year, it comes back exactly the same spot to the time and in a distance to the millisecond and the micromillimetre every year, and it's been doing it for thousands of years. And I think the error there was worked out at something like over a century is a few milliseconds, which ends up some error of I think it's 0.00 something with 13 zeros, 1%. So to me that is a divine system. That is divine, nothing we know of, nothing man-made or we can understand can end up with a number with 13 zeros after it. That's its greatest error. And how do we measure that? We can't even measure that. There's no instrument on this we know of that can measure that, just that the Earth does it. Which brings us to this question, why are we still using this perpetual motion modelling of the heliocentric system to describe our solar system. Okay, it's a big error there. There's a big question. Also, I said I'd bring in some Tartarian science. So now, there's a lot of this on the internet, so I won't go into too much detail, but basically the theory is that there was a advanced civilization, far advanced that we have today, and some remaining texts were left in buildings that remains from some cataclysmic event, some reset, and some texts were left over, which is not too strange. We have some very unusual buildings here built in Australia that were so-called built from convicts. These beautiful buildings, absolutely gorgeous. They're architecturally, their engineering is unbelievable, and they were built by half-starved convicts. Yeah, on a calorie intake that would feed a rat. Yeah, most of them were vagrants. There wasn't a skilled tradesman amongst them, probably very few. Now, how do you end up with skilled tradesmen out of employment? Like look today, look at any tradie. They're all driving around the latest vehicles, you don't find them stealing a loaf of bread. So, look, yeah, there's some questions about whether Galileo actually did come across some strange advanced texts from a civilization that he was actually trying to make sense of, and maybe the inclined plane was his way of interpreting it. The language would have been probably we wouldn't have been able to read it. Look, I know it's a far out thing there for me at the moment. I'm just playing with it, but I'm just looking at all angles at the moment. And not so unusual because, strangely enough, there's some evidence that also Newton was into ancient texts, and he had a massive library. Now, a lot of these ancient texts have been bought up by the private sector, and you will not find them in any of our libraries or our museums anymore. They're all in private collections, selling for hundreds of millions of dollars, so you won't get to see them, and if there's a secret in any of them, then you will not see them. Okay, the next video, I'll just we'll go into more detail on this 1.4 and why we're using it. So it's very important. Why aren't we using Galileo's 5 degrees? But anyway, we'll go into more detail. A little bit more on my Tartarian science, because it's one of my little things, I'll also bring in the zirconian ball bearing, which is half the weight of our steel ball bearing, so that should bring in some interesting results. So thanks very much for watching this video, and